Converting direction ratios to direction cosines. Now, before we jump into the formulas, let's quickly recap what we already know. In our previous lessons, we've seen that direction cosines, or DCs, are fantastic because they give us a unique, precise way to represent the orientation of a line in space. However, direction cosines are somewhat restricted because they must always satisfy a specific mathematical property. On the other hand, we have direction ratios, or doctors. These are much more flexible. You see, any set of numbers that is proportional to the direction cosines can act as direction ratios. This means we can scale them up or down, which is very useful in many geometric problems. In this tutorial, I am going to guide you through the step-by-step mathematical process of how we take those flexible direction ratios and convert them back into the standardized direction cosines. By the end of this session, you'll be able to perform this conversion with ease. Welcome, everyone. Today, we are going to dive into a very important topic in three-dimensional geometry, converting direction ratios to direction cosines. Understanding the relationship. First, let's establish our notation. We will represent the direction cosines of a line using the letters L, M, and N similarly. We will represent the direction ratios of that same line using the letters A, B, and C. The key to our entire derivation lies in the definition of direction ratios. As I mentioned in the previous slide, direction ratios are proportional to direction cosines. In mathematical terms, this means there is a non-zero constant, which we'll call k, that links them together. Specifically, L equals k times A, M equals k times B, and N equals k times C. Finally, there is one crucial property we must keep in mind as we move into the next slide to derive our formula. We know that the sum of the squares of the direction cosines is always equal to 1. That is, L squared plus M squared plus N squared equals 1. This property is what allows us to actually solve for that constant k in the next step. Now that we've introduced the concept of why we need this conversion, let's look at the mathematical relationship between these two sets of numbers. Deriving the conversion formula. Now that we understand the relationship between direction ratios and direction cosines from the previous slide, let's move on to the most important part, deriving the actual conversion formula. Our goal here is to find a way to calculate the values of L, M, and N using only the known values of A, B, and C. To do this, we are going to substitute our proportional values into the fundamental identity we just discussed. First, let's look at step 1. We take our expressions for L, M, and N, which are Ka, Kb, and Kc, and substitute them into the identity where the sum of the squares equals 1. This gives us Ka squared plus Kb squared plus Kc squared equals 1. In step 2, we simplify this expression by factoring out the common term, which is k squared. This leaves us with k squared multiplied by the quantity, a squared plus b squared plus c squared, all equaling 1. Now in step 3, we need to isolate k first. We rearrange the equation to solve for k squared, which gives us k squared equals 1 divided by the quantity, a squared plus b squared plus c squared. To find k itself, we take the square root of both sides. This results in k equals plus or minus the square root of 1 all over the square root of the quantity, a squared plus b squared plus c squared. Since the square root of 1 is just 1, we can simplify this to k equals plus or minus 1 over the square root of a squared plus b squared plus c squared. Finally, in step 4, we take this value of k and plug it back into our original proportional expressions. This gives us our final conversion formulas. For L, it is plus or minus a divided by the square root of a squared plus b squared plus c squared. Similarly, for M, it is plus or minus b divided by that same square root, and for N, it is plus or minus c divided by that same square root. Before we move on to the step-by-step process in the next slide, I want to highlight that plus or minus sign. It is crucial to remember that this sign indicates that a single line extends in two opposite directions. Depending on which specific direction of the line we are interested in, we would choose either the positive or the negative set of values. Step-by-step conversion process. Now that we have seen the mathematical derivation of our formula in the previous slide, let's break this down into a practical, step-by-step algorithm that you can use every time you encounter a problem. If you follow these 4 steps, you will never get lost in the calculation. First, you need to identify the direction ratios. This simply means looking at your given values and clearly noting down what a, b, and c are. It might seem trivial, but writing them down clearly prevents simple errors later on. Second, you must calculate the magnitude. This is a crucial step. You need to take each of those ratios, square them, sum them all up, and this is the part where many students slip up, take the square root of that total sum. You are essentially finding the square root of a squared plus b squared plus c squared. Think of this value as your scaling factor. Third, you divide each ratio. Once you have that magnitude we just calculated, take your original values of a, b, and c and divide each one by that magnitude. This process is what normalizes the numbers, shrinking them down so that the sum of their squares will eventually equal 1. Finally, you must assign the sign. As we noted in our derivation, the square root can be either positive or negative. Unless your problem specifically points you toward one direction, remember that a line extends in 2 opposite directions, so you should consider both the positive and negative sets. In the next slide, we are going to put this exact 4-step process into practice with a real-world engineering example to see how it all comes together. Illustrative example. Now that we have derived the formula and understood the step-by-step process, let's put everything we've learned into practice with a concrete example. Imagine a real-world scenario. An architect is designing a support cable for a stadium roof. This cable stretches from a base point on the ground to a specific point on the roof. To represent the orientation of this cable, we are given the direction ratios as 2, 3, and 6. However, the architect cannot work with just any proportional numbers. They need the direction cosines to calculate the precise angles the cable makes with the ground and the stadium walls. So, looking at our given values, we have the direction ratios where a equals 2, b equals 3, and c equals 6. Let's solve this step by step. In step 1, we need to calculate the sum of the squares of these ratios. We take 2 squared plus 3 squared plus 6 squared. This gives us 4 plus 9 plus 36, which totals 49. In step 2, we find the square root of that sum. The square backslash SQRT $49 is 7. This value, 7, is the magnitude we will use for our normalization. In step 3, we calculate the actual direction cosines by dividing each of our original ratios by this magnitude. So, L equals plus or minus 2 over 7, M equals plus or minus 3 over 7, and N equals plus or minus 6 over 7. Therefore, our final result shows that the direction cosines of the cable are plus or minus 2 over 7, plus or minus 3 over 7, and plus or minus 6 over 7. As we move to the next slide, I want you to pay close attention to the common pitfalls that students often encounter when performing these exact types of calculations. Common mistakes to avoid. First, let's talk about forgetting the square root. This is perhaps the most frequent mistake I see. When you are performing the division, do not simply divide the ratios by the sum of the squares, which is a squared plus b squared plus c squared. Instead, you must divide by the square root of that sum. Always remind yourself that you are dividing by the magnitude or the length of the vector. If you skip the square root, your direction cosines won't satisfy the fundamental property we discussed earlier. Second, be careful about ignoring the plus-minus sign. It is very tempting to just provide the positive values, but remember, a line extends in 2 opposite directions. Unless the problem specifically tells you to consider only one direction, both the positive and negative sets are mathematically relevant. As we saw in our derivation, the constant k can be either positive or negative. Finally, try not to confuse direction ratios with direction cosines. It is easy to get them mixed up when you are working quickly. Just remember, direction ratios can be any set of numbers, like 2, 3, and 6, as you saw in our architect example. However, direction cosines are special. They are normalized. they must always satisfy the condition that L squared plus M squared plus N squared equals 1. Now, before we wrap up our session with the final summary, I want to pause and discuss some common pitfalls. Even if you understand the formula, it is very easy to make small errors that can lead to incorrect answers in an exam. Keep these 3 points in mind, and you will avoid the most common traps in 3D geometry. Key takeaways. To wrap up our session today, let's review the key takeaways from this tutorial to ensure you have a solid grasp of the concept. First, let's revisit the idea of proportionality. As we discussed earlier, when looking at the relationship between these two sets of numbers, you can think of direction cosines as simply normalized direction ratios. This means we are taking those flexible ratios and scaling them down to a standard size. Second, remember the core formula we derived in slide 3. The entire conversion process boils down to one simple action, dividing each individual direction ratio by the magnitude, which is the square root of a squared plus b squared plus c squared. If you can calculate that square root, you can find your cosines. Third, I want you to connect this to what you already know about vectors. The process of normalization we just performed is essentially the same as converting any vector into a unit vector. We are taking a vector of any length and adjusting it so that its magnitude is exactly 1. Finally, let's keep in mind the concept of uniqueness. As we saw in our opening slide, a single line can be represented by infinitely many different sets of direction ratios because any proportional set will work. However, direction cosines are much more specific. A line has only 2 sets of direction cosines, representing the 2 opposite directions the line can travel. I hope this summary helps solidify these concepts in your mind. Great job following along today.